Okay, so here's about where we left off last time. So we've got in this example a parabola, and then we have a line. And the domain that we're interested in here is bounded by these two curves. And I can't remember if I may have started in on this last time, but let me just start over on this anyway. So very importantly, you have to interpret this in exactly the right way. So it does not mean just that the boundary of D consists of only these curves. That's not enough to uniquely identify the region. So for example, this region over here, the boundary of what I have in yellow there, the boundary consists of only the green curve and the blue curve. This is not the one that we mean, though. Likewise, this region over here and this region in here, neither of these is what we're talking about. So, bounded by furthermore means that the region itself is what we call bounded. In other words, that it doesn't extend infinitely in any direction. A really easy way to think of bounded is that you can put a fence around it of finite length. So there is only one actually bounded region whose boundary consists of only these two curves, and that's this right here. So heads up when you see this phrase here, bounded by, it does have this very specific meaning. Part of the question is to correctly interpret what the region is from this description. And again, make sure that what you claim is bounded by those curves, that you can put a finite length curve around it that entirely contains it. In other words, it can't extend infinitely in any direction. Okay, now with all that said, let's get to the integration aspect of this. Let's see, we're going to write a double integral as an iterated integral. In other words, we're going to only focus on the sort of the phase 2 part of the process here. Where this double integral came from, not part of this question. Maybe F is mass per unit area, and this is an integral computing mass. Maybe this is population per unit area, and this is an integral computing population. Whatever, doesn't matter, not part of the question. Okay, so here we go. I'm going to start off by doing the differentials in this order. We are subsequently going to do it in the other order, and then we're going to compare and speculate further on that, starting, though, with dx on the outside. X slices go like this. Here's what they look like, right? And, of course, the first one, then, is there. And let's ask, where did I come up with this minus 2 that I claim is the value of x? Of course, we're interested in values of x. Where did I get that minus 2 describing that point? Well, don't forget, that point is on that curve with that equation. And don't forget further, it is on that curve with that equation. Right? So this point that I'm interested in satisfies both of these equations. So both of those equations I can and should use as I'm trying to solve for x. So let's do that now. Let's take both of these equations, solve for x. Notice x is not hard to solve for. If x squared is equal to y and y is equal to 4, then x squared is equal to 4, which gives me two candidates. I could be looking for minus 2 or I could be looking for plus 2. Then you notice that the one I'm actually looking for here, notice that it's negative just from the picture. Thank you, picture, right? We need the picture to see, that this corner actually is, just again from the picture, it's on the left side of the y-axis. So because it's the negative one that I'm looking for, I know that this bound is minus 2. How are we doing? Everybody follow the process? Okay. All right. So upper bound, very similar. The upper bound is going to come from this point, which is on that curve with this equation and that curve with that equation. Same two equations. Same algebra. Same options. Only difference is that this time, again, thank you, picture. Clearly, the upper bound I'm looking for must be positive. Entirely interpreting that from the picture, and therefore we get positive 2. All right, is everybody good? Okay. All right. Now, inner bounds. We're going to, as usual, having determined our x bounds, we're going to fix a value of x, look at that one x slice, and then start thinking about the y bounds on just that slice. So, starting with the lower bound, comes from that point. That's our point, which is on this curve, which has that equation. All right, and now as usual, I need to solve. Don't lose track of what we're solving for. I'm solving for y. Good news, y is already solved for. It's x squared. Everybody okay? Now let's see here. The upper bound for y comes from this point, which is on this curve, which has that equation. Again, I need to solve for y, and again, it's already solved for. How handy. Sometimes you get lucky. So upper bound is 4. We doing okay? All right. Okay, let's do it the other way. Slicing in the other direction now. Doing dx dy. In other words, y slicing on the outside. Y slicing on the outside means we're slicing in that direction, which means our slices look like this. And first and last and all that, now I think that these end up being easier as it turns out. The first slice it's at the origin. Solving for y at the origin, I don't even really need to write anything down. It's the origin. Of course y is 0, so, easy one, freebie. This slice up here, the entire slice, I didn't even have to worry about which point I'm picking. The entire slice is on the line y equals 4, and thus y equals 4. Yeah, sometimes they're just right there looking at you. So that's convenient. The outer bounds, no problem. Is everybody happy? So, as usual, moving to the inside integral, we fix a value of y. Focus our attention on that one y slice. And now the x bounds, well, we'll start with the lower bound, which comes from this point, which is on this curve, which has this equation, and here's the landmine. Here's where a lot of students mess up. Very, very common for students to mess this up. Students will look at this and they'll say, oh, y equals x squared, so boom, x squared. You can see the temptation. It says x squared right there. It just seems like the clear answer. Always be careful to remember you have to remind yourself what is the variable I'm actually solving for here. I'm looking for an x bound here, and so in this equation I need to solve for x. X is not x squared. Y was x squared, but I'm not solving for y. What is x? X is going to be, plus or minus, I'm not sure, square root of y. Is everybody happy? Okay. Please don't step on that landmine. I've seen it a million times. And I always make a big deal out of it because hopefully we'll get that number down. Yes? For the previous one? Oh, for the outside?
No, one was the YPS.
Oh, okay. Yeah, okay, so we've got a value of x fixed, right? And you want the lower or the upper? Okay, well, so the lower bound comes from this point, which is on that curve, which has this equation. And reminding ourselves now, let's see here, we're looking for a y bound, right? We're trying to find our y bounds here. So in this equation, I need to solve for y. And lucky break, conveniently, it's already solved for. The equation already says y equals, and so y is x squared. Is that cool? Yeah. Okay. So upper bound, similarly, upper bound, this point, that curve, this equation, again, y already solved for, and 4. All right. Okay. So heads up on this landmine. It's really easy to lose track. And as you're solving for x, forget and think that, you just kind of look at the algebra and you see the x squared. It seems like an answer. And so a lot of people will put x squared there. It makes no sense and is also not correct. Don't forget to actually solve for the variable whose bound you're interested in. And that gives us these two options. Now notice, by the way, it's the same two options for both the lower bound and the upper bound, because both of these points are on the same curve, which of course has the same equation. And so one of them gives you lower, one of them gives you upper. Okay, so now having done this two different ways, we have then two different integrals, two different iterated integrals that will successfully compute this double integral that we were interested in the first place. Now, which one's better? And I maintain that one of them is almost certainly better than the other, even though they're both technically equal to this double integral. And specifically, I like this one better, because this one's got square roots in it. And it's tempting to say, well, who cares about these square roots? They're in the bounds. They're just going to be what I'm going to plug in after I've done the integral, but not really, right? They're part of the bounds for the inside integral. They're going to be what you plug in after you've done the x antipartial to evaluate this inside integral. In other words, said differently, they're part of your outside integrand. So you've got square roots in your integrand now for your dy integral. This is not good, right? We all remember single variable integration nightmares, right? And a lot of those nightmares featured the square roots, right? So this is not looking pretty. By comparison, this one over here, I've got a couple of polynomials there as part of this inside integral, but I don't know. I mean, it's not like it could have been nicer, but give my choice between polynomials and square roots, I'll take polynomials, strong odds over square roots. Okay. So, fine. Hopefully y'all believe me, this is the more desirable one, and the other one not so much. So, how do I tell the difference in advance, right? Wouldn't it be nice if I didn't have to actually crank out both iterated integrals before I can tell which one is the better one? That would be a good thing. So here's the idea. Let's look at what, in some sense, went wrong. Right? Where does these square roots come from? They came from the fact that I had to solve for x. I had to solve for x because x is the inside variable. And it was because I solved for x that I had to basically invert that function. Did everybody see that? So when you're looking at your various curves that describe your domain in one way or another, sometimes, such as in this case, the variables will kind of naturally, one of them will fairly clearly be an input variable, at least more naturally than the other, and one of them will be an output variable more comfortably and naturally than the other. And here I'm going to say I think it makes sense to think of x as the input variable. Well, whatever is going to be your input variable, you hopefully wouldn't have to solve for it. It's not an outside variable that I've already solved for. It's an input variable that I don't want to have to solve for it. So if you don't want to have to solve for it, don't put it on the inside. Is that cool? Does that make sense to everybody? Said differently, equivalent statement, kind of turning around backwards. Whatever variable is your output variable. And I love thinking of y as an output variable here because it's a nice function. Y is a polynomial function of x. Let that be the variable that you're going to have to solve for because it's already solved for one thing, but more importantly, it's something that's easy to solve for. So we put it on the inside where I have to solve for stuff, and again, that makes life easy. So, whichever point of view you prefer, they're equivalent points of view, but think in terms of which variable you'd like to solve for, which one you hope not to solve for, and let that guide your choice. Okay. All right, here's another example. Got a triangle with certain corners, like this here. Again, we've got two different ways that we can go. This one here, doing dy on on the outside. Y slices are that way. The Y slices look like this. They start there, they end there. Pretty easy to see that goes from 0 to 1. Skipping over the details, but I'm going to let you all fill in those blanks. I think it's not hard to see. And then let's see, for a given value of Y, let's think now about the range of values of X. Well, the lower bound comes from that point, which is on that curve, which has the equation X equals Y. And the upper bound comes from that point, which is on that curve, which comes from the equation X equals 2 minus Y. So this top ordering of the differentials, the iterated integral works out like that, nice and easy. Everybody happy? Yep. Well, I mean, okay, yeah, I know what you're saying, right? But so one thing you have to keep in mind is that when we're finding inside variable bounds, right, we're only looking at a single value of the outside variable. So we're just looking on one Y slice at a time. So remember, think back to the very beginning when we were taking slices of volume, right? The purpose of the inside integral here is to compute a cross-sectional area at a single value of Y, right? Now, you point out correctly, look, sometimes X is as low as 0, right? I mean, like this point here. And you're right, X gets arbitrarily close to 0, and we'll get there. We will get that point. We get that point for this value of Y, right, which has X going from sort of there to there. So it all gets accounted for, but we don't want to know the overall bounds on X. We want to know the bounds on X as functions of Y. Yeah, it's a good observation. Okay. So let's slice it up in the other direction, see what happens. And something pretty uncomfortable happens here, honestly. So I'm going to start by slicing, again, in the X direction. Our slices look like this. And it's tempting to say we go from 0 to 2. There's a problem. The problem is that for these values of X between 0 and 1, let's think about the inside bounds for those values of X, and let's think specifically about the upper bound for Y. The upper bound for Y is at that point, which is on that curve. Well, it's on that curve at least for these values of X. But for further values of X, over here, this is no longer the correct curve for me to find my upper values of Y, right? My upper values of Y for those values of X is it's not any of this stuff up here. It's, well, this point, which is on that curve. Right, so I have to represent that by saying that wrong color. Separately, I'll consider X being between 0 and 1, and then separately from that, I will consider, cleaning up my mess, we'll consider X being between 1 and 2, because for these for these greater values of X, the upper bound for Y is Y equals 2 minus X per that curve, as opposed to Y equals X per that curve. What do you think? Yep.
Would it be possible to write that as an expression involving absolute value?
Maybe, probably, but I'm going to say that buys us nothing, because then how do we deal with those absolute values when it comes to actually cranking out the integral? Well, I'd have to separate it, because absolute value, there's no convenient formulas for integrals involving absolute values. So, effectively doesn't really buy us anything. It's a good thought, though. Yep.
Just so, like, similar to the last one, we're getting integers as a function of another variable.
Yep.
So here we're using the equations of the given line.
Here we're using what?
Like the equations of the line.
Yep. Yeah, that's right. Yeah, exactly. Yep. Right. Okay, so, all right, so who's to blame for this catastrophe that we have here? And I'm going to put it like this. I'm going to say that the problem is this corner. Ultimately, that's kind of the problem. The point that we used to define the upper bound for y, trying to find the upper bound for y, these points jumped from that one curve with one equation for a little while over to this curve with a completely different equation, and that jump happened at this corner, and it happened at that corner because I sliced through that corner as I proceeded to slice in the x direction. So it's because, again, I blame the corner is what made me have to stop my integral at x equals 1 and resume from x equals 1 onward, because that's what gave me the different formulas for those y upper bounds. So there's a nice little upshot here, is try not to slice through corners. I mean, it's pretty easy to anticipate in advance. You can look at this picture and just kind of immediately see that if I slice in the if I slice in the x direction on the outside, those x slices hit the corner, at which point I have to say, all right, okay, well, fine, but now beyond there, I've got a totally different story. So just try not to slice through corners, and this problem won't come up. And again, highly profitable to avoid this kind of situation, because this situation, it made me had to compute two separate integrals, as opposed to, wouldn't it be much nicer just to have the one integral to compute, all else being equal. Okay. Is everybody happy? So we got two morals, strategic morals, I'll say. Think carefully about which variable is the input and which one's the output, and choose your order of differentials accordingly, if you can, all else being equal. And try not to slice through corners, again, all else being equal. These are great sort of guidelines, unofficial, not always, all exceptions granted, but very few exceptions. Actually, when one of these rules speaks to one order of the differentials over the other, it's probably the right choice. Okay. All right. Next example. Just doing a bunch of examples here. Show you the kinds of issues that can come up. Suppose we want to find the volume in between this paraboloid and this plane. And you can see I have the volume in between drawn separately over here, because it's a little bit easier to kind of see what's going on over there. Everybody good? Okay. Broad strokes. If I want to know that volume, I'm going to view the volume as being the sum of the volumes of a bunch of little French fries. I claim that the volume of the French fry is easy to write down because it's this height, which is the difference of these two z coordinates, times the area of this little base down here, which of course is the area dA that I'm chopping up the domain into here. And so height times the area of the base gives me little pieces of volume. The whole volume is the sum of the pieces of volume, and done. We have almost all of a double integral already written down. Seemingly everything's fine. There is the one sticky wicket here, and that is I don't have any indication yet what my domain is for this integral. Right? It doesn't say in the statement of the question, find the volume in between these two surfaces sitting over a particular region. There's no comment. The implication is we want the entire volume between these two surfaces. So I have to then decide what is this region down here. What is this? You might say this shadow down here in the XY plane. What is the projection of our solid, in other words, down into that XY plane for this solid? Everybody see the problem? Okay. So here's how you deal with this. Reminder, for a point like this one, there is the height up to the plane, which I'm calling Z2, and then there is the height up to the paraboloid that I'm calling Z1. Okay. Let me show you first, before I go on with that, let me show you the mistake, the landmine. Here's what a lot of students do wrong. A lot of students will look at this and say, look, what I really want is I want to know where are these points along this curve. I want to know the boundary of my domain. That's just going to come from this curve up here where these two surfaces intersect. Where the surfaces intersect, I want both equations to be true. And then they speculate or reason, well, then I guess I want to set these two equations equal to each other, right? I mean, just thinking casually, if you want two equations to both be true, shouldn't you set them equal? And it's very tempting, and it's also complete nonsense. You may be wondering now, why have I never heard the phrase, let's set these equations equal to each other, right? Probably never heard that in a math class, because it's not a thing. Right? And just for humor value, I like to elaborate on how ridiculous it is with the following. Here's a true equation, and here is another true equation. If I want them to both be true at the same time, should I set them equal to each other? No, of course not. That's total nonsense. Right? Not to mention the fact that, look, if this equation is true, then I can add 1 to both sides. So should I set 3 equal to 7, or maybe I should set 3 equal to 8? Right? It just doesn't make any sense at all. It's just nonsense. Okay, so don't make the mistake of setting equations equal to each other. It's not a thing, and that's not how you proceed here. As we noted down here, keep in mind that, actually, let me zoom back in here. What I'm looking for is for these points. I'm looking for these points that are on this boundary that namely go up to this curve, this intersection curve. And that intersection curve happens where the height up to the plane and the height up to the paraboloid are the same. So, in the interior of our domain, Z2 is going to be bigger than Z1. But on the boundary of the domain, Z2 and Z1 have to be equal. That's what it means for these two surfaces to intersect on this kind of edge curve, is that these two heights are the same. Geometric appeal, does everybody buy it? And that suggests, algebraically then, it's not that I'm going to set the equations equal to each other, it's that I should set the two z's equal to each other. I should set this equal to that, which apparently I'm going to have to solve for. And that's something we can do directly. Solving for z on the left is x squared plus y squared. Solving for z in the equation for the plane on the right, and a little bit of work to be done, but if you solve for that z in the plane equation, you get this thing over here. And now, this then is the proper algebra to deal with. And having set those two things equal, by the way, completing the square, I'm going to repeat a recommendation I made some time ago. Completing the square is really useful on a pretty regular basis. Don't make the mistake that I made when I was in middle school, high school, whatever that was. Somebody pointed out to me, oh, you don't really need to complete the square because the quadratic equation kind of obviates that. You don't really need to just memorize the quadratic equation. You're good. That only works if you're finding roots of your quadratic. That's not what we're doing here. Right? We're doing a different kind of algebra with quadratics. So this idea that we don't need to be able to complete the square just doesn't hold water. So make sure you're good with completing the square. If you're rusty on it, if you're not sure how that works, whatever, come to my office hours. I'll be happy to show you. I'm sure you can also look it up online or whatever, but make sure you're good at that. Yes?
Could I set any of the variables equal to each other given,
I hear where you're coming from. Here's the thing, though. There's something unavoidably sort of in this direction about the question, right? So, in other words, these things here, these French fries, are vertical French fries, right? And I'm talking about their, sort of heights. This height minus that height, because that's what's associated to a piece of area down here in the XY projection. And so once I've made that decision, which by the way is the only really good decision here, because you have the French fries going the other way, everything gets weird, right? So once you decided to go vertically like this, then you're kind of stuck in needing to find the X's and Y's that give you the appropriate Z's. Now, in a different question with different geometry, where perhaps you could choose to orient it in other ways, then yeah, totally. You probably have options.
Geometrically, this is the most convenient.
Geometrically, this is the most convenient. Yeah, you're going to have all sorts of much worse problems if you try to orient your French fries parallel to the y-axis. Yeah, there's some ugly aspects of that's going to be highly undesirable. Yeah. That's right. You'd need to solve for y as a function of x and z, and it's going to be a nightmare of multiple inconveniences. Yeah. Right. Okay. So anyway, that's how this one works out. Just be aware. Sometimes you have to find the domain on your own. This is an example of how that can work. And that does it for section 5.2. We're going to move on now to 5.3, which we're going to spend all of about 5 minutes on. This is the shortest, one of the shortest anyway. There's some other short ones, but one of the shortest sections in the book that we're going to cover. Strong case could be made. This could be a concluding example in 5.2, but doesn't matter. There's really only one big idea in this section, and that is that when you are asked to compute an iterated integral, just remember that iterated integral came from a double integral. There is an underlying double integral that this is a tool for computing. So if you have problems with your iterated integral, you can interpret that as saying, you know what, the underlying double integral here, somebody made a bad choice of which way to slice. And I'm just going to make a different choice of which way to slice. And all you have to do is reverse engineer, figure out what that original double integral is, and then slice it the other way. So that's the big idea here. First, let me show you what's ugly about this iterated integral. Why do I not like this one? And if you look at the inside integral, well, you can't do that integral. You can't. There is no convenient, let's say, antiderivative of e to the x squared. It's a weird fact. It's hard to prove in this context. We're not going to prove it here, but I claim if you try to find an antiderivative of e to the x squared, you're going to lose. You just can't do it. Weird. Okay, so this is a bad order to slice. What double integral did this come from so that I can slice it the other way? Well, again, reverse engineering. I see that the y bounds are from 0 to 1. Well, geometrically, that's what that means. My domain must be between y equals 0 and y equals 1. So it's, something in here. Okay. Now, furthermore, I have to zoom out a little bit here. The x bounds our x equals to y, which is that line. Let's try that again. Boom, there you go, that line. And then my upper bound for x is x equals to 1, which is that line. And so what we have then, coming back down here and putting it all together, for every value of y between 0 and 1, I'm going to go from the light blue line over here to the dark blue line, and all together, that gives me this yellow region as my original domain. So I've successfully reverse engineered and found my original domain. Everybody okay? So with that done, I reinterpret the question I was asked as computing this double integral, where D is understood to be this domain. I realized that the original order of slicing was catastrophe, so I'm not going to slice it in that order. Let's just slice it in the other order. Let's do dy dx instead of dx dy. See what happens. Might get lucky. Couldn't be worse than what we had before, I suppose. So here we go. Okay, so x, what's the range of values of x? Well, we start with x equals 0. We end at x equals 1, which I read straight off my picture having come from reverse engineering the original integral. Then we fix a value of x, somewhere between 0 and 1. The lower bound from y comes from this point, which is on that curve, which has that equation. We solve for y, and y equals 0. The upper bound for y comes from this point, which is on this curve, which has equation y equals x, which gives me that upper bound for y. Now all I've done here is just re-slice in the other order. Now I've got a totally new iterated integral, and let's try to now see, is this better or worse? Is this a good thing? Was this a complete waste of time? And I claim that even though at a glance this continues to look horrible, it looks like we're still taking an integral of e to the x squared, for crying out loud, right? But we're taking an integral with respect to y. So y is our variable. X, you will notice, is the outside variable. That means that x is constant for this integral. That means that e to the x squared is a great big constant, and we are taking here an integral of a constant with respect to y. World's easiest integral. And you antiderivative, plug in x and 0 and subtract, etc. And this integral turns into this, which is itself easy to integrate by doing that substitution. So it just falls apart into nothingness because we switched the order. What do you think? Is everybody on board? Again, this is the one little sort of weird trick, and there are a few circumstances where this comes up, and all it really is remembering where iterated integrals come from. Iterated integrals are tools for computing double integrals. Find then what double integral does it represent, and slice it the other direction. Cool. That was 5.3. Moving along, 5.4. Okay, triple integrals. So taking stock real quick. We came into this class knowing single variable integrals. Single variable integrals compute things that add up over an interval. Right? A one-dimensional interval is our domain. We think of quantities that are distributed over a one-dimensional interval on the x-axis, t-axis, whatever. Okay. Then, a week ago, or whenever that was, we entertained the more complicated question of what if your quantity, instead of being distributed over a one-dimensional interval, what if it's distributed over an area? Right? So, you can talk about, for example, the mass of a one-dimensional rod. If you think of the rod is just, mass per unit length is distributed across the length. And obviously it's not actually one-dimensional. Obviously a rod has some thickness to it, but still, if you have a metal rod, very often the metal rod's only job is to be a certain length, right? And the actual thickness of it, who cares? Its job is to be a certain length. The mass I think of as distributed across the length, and the actual width and depth of who cares? It's just easier to think of it as being one-dimensional. So, on the other hand, you could have mass or population or any other quantity distributed across an area. This is a fundamentally two-dimensional thing, not one-dimensional. And so, we had to come up with a new idea of a Riemann sum because the quantities are distributed across two-dimensional regions instead of one-dimensional regions. And you can probably see this coming. Triple integrals are what we get if we're going to add things up that are distributed over a three-dimensional region. So, again, metal rod, we think of the mass as distributed one-dimensionally, whether it really is or not, whatever. Double integral, we think of population or mass distributed two-dimensionally. The real world, if you think about it, most things actually live in three-dimensional regions, right? If I have a fish tank and it has of a certain shape and it's got a certain amount of water in it, I want to compute the mass of water in that fish tank, or I want to compute the amount of algae that has grown in the water, or whatever, distributed over a three-dimensional region. Yeah, I think of that as something that's distributed over volume, not as something that's distributed over area. So what we're going to do is basically the same as double integrals. Chop it up, add it up. It's just that instead of chopping up a one-dimensional interval into subintervals or a two-dimensional region into sub-rectangles, we're going to chop up a three-dimensional solid like this into what I'm going to call sub-boxes. And then I'm going to argue that, on the sub-boxes, the answer to the question is typically pretty straightforward. If this were mass that I'm interested in, I'm going to compute the amount of mass in this box. Maybe it's more dense kind of in this corner, and it's less dense up here in the upper right, or what have you. Yeah, but in this little teeny tiny little sub-box, it's a very small little sub-box. The density is approximately constant on that little box. And mass per unit volume times volume should tell me how much mass is in that piece. And if I know how much mass is in each little piece, then I can add up over all the pieces. So that's the big idea. Details to follow, of course. Is everybody on board so far? Okay. All right, we've already talked about how to, what are the details if you're chopping up an interval on the x-axis, chopping up an interval on the y-axis. That's old news. We did that for single variable integral. Well, we did this part anyway for single variable integrals. We did this part when we started doing double integrals. And now that we're doing triple integrals, all that's the same, and I just need to know how to chop up this integral on the z-axis. It's morally equivalent. Right? It's still an interval of a certain length that I'm chopping into in pieces. So I have a delta z. And then successively, as I go from each, z point to the next one, I'm adding an extra delta z every time. So same structure of formulas as the formulas on the x-axis, formulas on the y-axis, same deal, different details. And that then makes everything precise as I write down the following definition. Here we go. This is going to be our strategy for computation. This right here is our strategy for computation if we have a question involving a quantity that's distributed over a volume. Take your volume, chop it up into little boxes, sub-boxes. On each little box, we'll take quantity per unit volume times volume. right? Delta X, delta Y, delta Z is the volume of the sub box. So quantity per unit volume times volume gives me the quantity in that box. Let's see here. This is the quantity within each box. And then I add up over all the boxes. And I have an answer to the question. Whoops. I'm trying to erase yeah, there we go. Everybody with me? All right. Okay, so terminology, notation, let's get this all said. Triple integral. That's what this expression is. I mean, it's a Riemann sum, but this is what we mean when we say triple integral. And yes, we also have a notation for it, and that's convenient, and that's, of course, what everybody uses, and I encourage you to use this notation, but I want you to make sure to remember this phrase, triple integral, means Riemann sum, this kind of a Riemann sum, specifically that there is a three-dimensional domain in question. It's been chopped up into little sub-boxes, on each of which we can talk about quantity per unit volume that we can then multiply by volume to compute quantities, which I then add up over all the boxes. That's all that means. Now, how to compute this? Oh, that's a different question. We'll get to that in a few. But what does triple integral means? It means this strategy, you chop it up, add it up over a volume. Okay. Alrighty, just like with double integrals, y'all are not responsible for the business about irregular partitions and test points. Just, feel free to ignore, look at only to the extent that your curiosity would have you look at it. Which is because, in fact, for continuous integrands, it really doesn't matter. Okay. Alright. Okay, so now here's our motivating example that I'm going to basically kind of repeat because it's a repetition because this was what motivated our construction in the first place, but let's go ahead and repeat it to get a clear answer. If you do want to compute mass in a three-dimensional region, where you know mass per unit volume, step one, mass accumulates. The total amount of mass is the sum of all the little pieces of mass you break it up into. All right, the whole is the sum of the parts, is all that says. And what is the mass in one of these little pieces? Well, mass is mass per unit volume times volume. And so, as planned, we have a triple integral. All right, now probably the last thing we're going to be able to do today before we go on, I want to remind y'all in single variable calculus, the vast majority of single variable calculus students like to hang their hat on the area point of view of thinking about single variable integrals. In other words, that this is the primary cornerstone example of an integral is computing area under a curve, and I've already made the complaint that I think this is overappreciated. It's not that it's wrong. It's not even that it's bad. It's just overappreciated. It is to be appreciated, but I think the students maybe appreciate it a little too much. And I think this point of view is underappreciated. The reason why is thinking about, for example, mass distributed across a one-dimensional interval. We have intrinsically an expression that is all about accumulation over one-dimensional intervals. And here's an example where the whole picture is likewise on a one-dimensional interval. This is much more compatible with the one-dimensionality that really is what a single variable interval is about. Right? And this two-dimensional problem is, I suppose it's geometrically satisfying and it's useful to visualize certain aspects of integrals, and I'm all for it, but it has its limitations. One-dimensional integral, one-dimensional metaphor, two-dimensional metaphor, so pros and cons. Now let's go to double integrals. Double integrals, mass distributed over a region, two-dimensional picture, volume under a graph, three-dimensional picture. And again, pros and cons, and yes, there's something very satisfying about this, and again, I'm not against it, I just, wish there were more focus on this point of view instead. It's, currently about like this, and I'd like to get it to about like this. Right? I'm not saying zero, right? But maybe just a little bit more balanced. So here's one of my big reasons. Now I've already talked about the dimensionality agreement is a big deal. This is really a more natural, a more honest way to understand integrals. Yeah, fine. But let's extend the analogy here, extend the metaphor for triple integrals. Mass distributed across a solid three-dimensional region. Fine. Cool. Three-dimensional picture. Volume under a graph? Wait a minute. What? It's not even a volume. This is now a four-dimensional thing. Four-dimensional volume? Whatever that means. I can't visualize the graph for this to even be useful as a picture. This is a completely... that didn't really come through. Let's just do it like that. Completely useless concept. Right? Yes.
The function was one. Would that just be the volume?
It is, but really more naturally because of this reason than that reason over there, right? I would think of if the density is 1, right? Then if density is 1, then a mass computation is volume, and so really a more natural picture. But yeah, totally. So yet another reason to think more in terms of the mass metaphor and less in terms of the graph metaphor, right? And here's the worst part of it, and then we'll call it a day. Here's what happens to a lot of students. A lot of students think of single variables and integrals this way, double integrals this way, and then triple integrals this way. And then they get confused as to why is it that I have a three-dimensional picture for understanding double integrals and a three-dimensional picture for understanding triple integrals. What gives? How come it's the same dimension picture but for different algebraic constructions? And how do I know when I've got a double integral and when I've got a triple integral? And it would be very natural to be confused about this. The problem is we're doing an apples and oranges comparison, right? And so yet another reason to kind of, let go, distance yourself from this point of view. I'm not saying let go of it completely, but try to think more in terms of that picture for single variable integrals, that picture for double integrals, and then this picture for triple integrals is a natural extension. The analogy continues exactly as you would think, and it's just all happy. Does that make sense to everybody? So, for your consideration, good to see you all. Have a nice day. Drawing a line right there, and we'll pick up here on Wednesday. Have a good one. And as usual, don't forget to stick around and make sure I mark you down for attendance.